We're going to start the AI vibe. We're going to start the AI spine coding intro in just a minute. I'm just posting it on some channels here. Spine programming. I'm going to teach you all about spine programming. Check out github.com/computate-org/computate for more details. Check out the updated README. Spine programming. Spine programming stands for spine programming is not easy. And we're going to do our Halloween demo today, celebrating 20 years of spine coding. Let me just add a picture to this post. Started in just a minute. Okay. I posted that on my Red Hat Research Slack and Computate Slack. Spine programming. Okay, and make sure these links work. Yes, okay. Okay, and this. Okay. Let's see, a few more. Okay, one more channel. I'm going to some files, spine coding. Okay, here we go. Welcome to today's webinar where we're going to be doing some spine coding, and I'm going to teach you all about what that's about. Let me share my screen. So I've updated the README at github.com/computate-org/computate about spine programming. But we've been doing this for 20 years, developing all sorts of data-driven websites over the years. To show you where it all began, you can go to the web.archive.org and search for trailblazehunting.com and go back to 2005, and you'll see that way back around Halloween of 2005 was the launch of my very first website. It was called trailblazehunting.com. and it's a hunting consulting company who needed a website. And this site is still running in production today after all these years at troubleshunt.com. And this was spine coded back then with completely in XML. And today we do spine coding in reactive Java asynchronous frameworks like Vertex. So today I want to show you how we spine code the AI Telemetry platform. And here is the AI Telemetry platform. We developed this in OpenShift AI in a VS Code workbench in the Mass Open Cloud. So everybody gets access to their own workbench here on my team, on our observability team. And we developed this application. And to show you what it's like, let me hide this video panel and then show you how we can stop and start this application. So we go to the Run and Debug tab here. And if I go to this page right here, this is the current page, but if I refresh, it's going to crash. It says application not available because I stopped it here. So I can run this application in VS Code in OpenShift AI, and it's going to start up. It's going to connect to Zookeeper Cluster Manager. It's going to connect to the database. It's going to connect to Keycloak, and it's going to import a bunch of data from our observability metrics in OpenShift. We have 3 OpenShift Advanced Cluster Management Hub clusters with many, many clusters attached to them. And it goes and imports the data, and then it's accessible from a route that's made available. So I can do live development of this site within OpenShift AI, all in the cloud, just by using a browser. It's pretty powerful. But let me show you how this virtual machine page was created using spine coding. So I'm going to break everything here. What I'm going to do is delete all of this virtual machine code here. This is where it all began with the spine coding. And I'm going to delete all of this and break up my whole application. There's some more. There's virtual machine gen.java. Let's see. For some reason, it doesn't want to show it to me in that view. So let me go directly here. Virtual machine. So these classes were spine coded. I'm going to delete these. Now, what happens if I try to stop and start this application? If I try to start it, it says build failed. And there's all of these errors now because virtual machine doesn't exist anymore. It's not a Java model anymore. If I check the main vertical where everything starts and I look for virtual machine, let's go to the top. It shows these classes missing. So let's build this back again with spine programming. So we go to our source main Java. I have 2 source directories. You see I have the gen directory, which is generated, completely generated code, and then the main directory, which is some non-generated code, some code written by hand, and some code that is spine generated. So we go back to this virtual machine directory, and we're going to add a Java class called virtual machine.java. Now, this is nothing special, just has a package and a public class virtual machine. I'm going to bring in some imports that we need. So I have the original source code here. I'm just going to put it to the side and maybe, oops, maybe, gotta shrink this somehow. There we go. I don't need all that space. I want more space in VS Code. So bring in some imports, import, and paste those imports. So we have those. Those imports all exist. There are going to be some things we reference below. Now, I'm going to start to describe this class. So here we go. We're going to give this an order in the API because in the user interface, or as we declare these models, we want them to be ordered in a certain way. So if I do Control-Shift-F and I search for star order colon, you'll see some other orders that I've given to other models like 0, 4, 1. I'm going to give this model virtual machine an order of 17. And I'm going to give it a description of a Red Hat OpenShift virtual machine. Now, this is just a Java comment, but we can use Java comments to our advantage to do some spine coding. We give it some language context so that some in English, some words you start with the letter A and then virtual machine. Some you do an. And so this is just some language context that we can do to help our Java code create some user interfaces that describe our virtual machine correctly according to the English language. Although this vibe coding platform is completely supported in the French language as well. Now we're going to give this a Font Awesome icon because I'm a Font Awesome subscriber and I absolutely love Font Awesome icons. So we just paste in Font Awesome icon for sidebar here. And then we're going to add some sorts. So when we sort this virtual machine, we're going to sort it by the hub identifier, the Red Hat Advanced Cluster Management hub ID, followed by the cluster name, followed by the VM project that it's in, and then the VM name. So we had 4 different sorts to our class. And we have our API return 100 rows by default. So we can show up to 100 rows at one time in our user interface. We can actually show more if we want to, but by default, it'll show 100 rows. And then we're going to describe some APIs that we're going to build for our virtual machine model. I'm going to paste these in and describe them. So we're building a search page where you can search for VMs. That was the page I showed you earlier. This is the search page where you can filter and sort and get some stats on your virtual machines. And we have an edit page where you can edit an individual virtual machine by its VM resource identifier. And a user page, well, we might use this later for something. I think we could actually remove it, but I'll just leave it in here to keep things the way they were before. And then an API URI. So this is a JSON API endpoint that you can query the data with JSON. Now, all of these pages are backed by fine-grained access control. Oh, we'll talk about that in a sec. We're going to create some more APIs to search the virtual machines, which will be accessible at this API URI by default. And then you'll be able to get an individual VM at this API URI with a VM resource after that. Just so you know, You can also patch multiple virtual machines at the same time, and you can create new virtual machines with this API and a delete API and an import API using the put method. Now for access control. We define the access control to virtual machines using this syntax in the code comment. So we specify auth groups, and we say that a hub admin can get all virtual machines, and an admin can get all virtual machines, and a super admin can also get all virtual machines, but it can also create, patch, delete, and do super admin things on virtual machines. So we have defined our class. Now, this is still just a class with the Java. It's just a regular Java class. We need to turn it into a spine coded class. And so the way we do that is we do extends virtual machine gen, and we tell it what the class underneath this imaginary class virtual machine gen should be, and it'll be base model, because that's a class we have. Other classes we have are also base models, like cluster.java. So cluster.java is a similar one that describes OpenShift clusters, and it extends cluster gen, which extends base model. We use Java generics for a powerful solution to spine coding that lets us generate a class that extends another class from this declaration here. So watch what happens. It says there's no virtual machine gen, but what we have is a service that's running. It's the Computate code generation watcher service. Let me kill this and show you what it is. So it's just this script called bin/watchnow.sh. And we run the script, and it's going to connect to a Zookeeper cluster manager so that it can do file locks to make sure that it's not regenerating code that it doesn't need to at the same time as something else that's happening. So it does some smart little file locking to prevent unnecessary changes. And it says that it's watching this directory, the op/app-root/src AI Telemetry source main Java source directory /org/mghpc/AI Telemetry. And let me just add one of these spine-coded methods here before we do the next step. It's good to add at least one spine-coded method right now, because this is our spine, and each of these vertebrae is a protected void method. This is a cool syntax that lets protected means that the class can access it, and all of the classes that extend this can access this method. So I put an underscore, and this is where the word spine is relevant, because this is like the disk between your spine vertebrae. You put a little underscore to describe that this method is going to be a spine-coded method, because you can put other methods in here that mean nothing at all. But if it starts with the underscore, or you put a disk in there, then it's going to be a spine-coded method. And so we describe hub ID, and we tell it to be stored in the search engine with this concept called doc values. Doc values is a very efficient way to store things in Apache Solr, our search engine. We do persistence in the database with normalized data, which is like the raw data that we store in the database for a virtual machine. But we also And that's why we do persist true, because it's persisted in the database. We also cache it in the search engine with doc values. And our Apache Solr search engine is so good at querying and filtering and paginating and faceting and getting stats on fields that it makes a very powerful cache. So we declare how we want it to be stored in the search engine with doc values, true, and then we can do we can, when we save this data, it'll enter a database transaction and be committed in the database. And then if everything goes well with the input, then it will put the data in the database, and then we will put the data in the search engine in another commit to the search engine, and then we will close the transaction. If everything goes well, we'll commit the transaction. If something fails, we'll roll everything back and nothing will go into the search engine or the database. That's how this persistence works in this application. But we also describe a display name of this hub ID as ACM hub, and we give it a description, the name of the ACM hub for this cluster in a Prometheus Keycloak proxy. And we put the place for this field on the edit page of a virtual machine using this syntax here. We'll go into more details on other videos, but we'll also create a row for this in the user interface called virtual machine details. And we'll say that we can gather facets in the search engine for this field. And so I save this. Now watch what happens when I save. We're going to have the watcher service recognize that this file was saved. So I save this and it says class virtual machine touched. And wait for it. This is fast. Developing this spine coding is faster on your own computer, but it also works in the cloud. It's just a little bit slower because there's less threads available on this machine to handle this. But you see, it created a new class called virtual machine page touched. And it says class virtual machine generated and class virtual machine page generated. So it did some code generation for us. And we should see this, this imaginary class become available any moment after this workbench, cloud workbench, has a chance to discover what just happened. So look in the files. These files just appeared. We have some API. We have some API interfaces and implementation classes for this virtual machine that just appeared, as well as some generated code inside of source gen model virtual machine that we already deleted earlier. So if I go here to virtual machine gen, it created this big class that's 782 lines of code that has getters and setters and serialization type methods to help us turn this into a data-driven API and website. And this class that didn't used to exist is now available. We were just looking at it. So it also auto-generates some documentation about this so that I can hover over this generated class and learn about this virtual machine and what happened about the virtual machine class and its generated class virtual machine gen. So you can go and read more about it directly in the source code. And nothing that happened here goes to some cloud service somewhere. This is all happening on your own computer or in your own sovereign environment. And for that, it's our OpenShift cluster. Everything stays within our project, our AI Telemetry project within our OpenShift cluster here. So this is a secure way to generate code. And what happens under the hood is everything gets stored in the search engine I was talking about. So inside of our OpenShift environment, we have this Solr collection that has it has a collection called Computate because my username is Computate and Computate is this code generation software. And if I do a filter query on a virtual machine, then it shows that there's two records related to the virtual machine class. And this is all of the language context. This is like an AI model for your code. And and it knows everything about every piece of code in the whole project and can link things together and generate code for you because it has all this data in its own database model, but it's stored in a search engine, which is a very smart place to put information about your code because it's your own API for your code, which is really powerful. And so so this virtual machine gen class was generated from this record in Solr. So it knows our class, the class that it extends, like virtual machine gen, and the other class it extends, which is base model. And it keeps track of all that information and all the comments and parses them and does some intelligent things. So I'm gonna just sometimes when you generate code, you want to generate it 2 or 3 times so that it makes any relationships correctly when it generates it, because it generated this virtual machine page class, but it's not perfect the first time it's generated. It needs to be generated one more time before it kind of reaches perfection. So the other thing about this cloud pod environment is it doesn't always pick up that your file was changed. That's why it helps to watch the logs to see if you get this message that your virtual machine class was touched. Because I saved it again, but it didn't pick up that it's saved. And that's just kind of a quirk of this cloud environment. But so let's see. So it's having problems with the code generation because we haven't given it everything it needs to be an API. We need to add the rest of these methods. Let me show you what they are real quick. I want to wrap this video up, so I won't go into super detail, but we specify a hub authorization resource, which has some specific fields that are required to relate it to a hub, and then cluster name, a cluster resource, authorization resource, a virtual machine project, which is a namespace thing in Kubernetes, and then a virtual machine name, an operating system, a virtual machine resource for authorization, a virtual machine display name, a description, some where this appears on a map with colors and titles and links, and GeoJSON to put this on a map somewhere of where this virtual machine actually lives in a data center. And then a unique ID for this called the entity ID and entity short ID and some NGSI LD tenant data, which helps with multi-tenancy in a standard that Fireware organization has created. So I'm going to add the rest of these fields to complete our model. And then we shouldn't see any code generation errors in the spine coding. So we go like this. Also, I want to change tabs to spaces. So that's my new favorite. And save this class. And let's check how this is doing. So it says class virtual machine touched. And Wait for it. And now the virtual machine class has been generated, and it generated uh, this Java interface that has all the methods that we described in here at the top. We described an edit page URI, a user page, an API with search, get, patch, post, delete, and import. And it went and set up these interfaces for us to search and get and patch and post and delete and import and pages for us. So then this interface is, we create a class that allows you to, we create the whole API in Java Vertex reactive asynchronous code. So we created a spine. Think of this as the vertebrae where we have built an asynchronous, we've built all this asynchronous code that's reactive because it involves futures and promises and on success and on failure methods that gets very deeply nested, but just think of it as like your skeleton or your spine for the whole application. It's really fun to write reactive code, and it's fast and efficient and scalable. So we created an API for searching, for getting an individual virtual machine, for patching virtual machines, for posting new ones, and deleting virtual machines, and importing virtual machines, and the search page, and the edit page, and the user page, and filter, delete, and some general methods. And it's 4,000 lines of code. And we'll also, because we have indexed all the information about virtual machines, we used to only have 2 pieces of information, but now let's execute this query. Now there's 22 things found about this class. Those 22 things are these 22 methods in here. Hub ID is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 20. I must have missed. Oh, 22 is the class itself. So there's 22 items, and it's a lot of data. If I just scroll and scroll and scroll, you'll see there's like massive amounts of information about this class. And it was all created in like a second. And it's so easy to query. And you can write so much code this way. It's so powerful. So we've generated this, and now we need to rebuild our API because there's some stuff that happens outside of these Java classes, like building the Open API spec and building the database create scripts that involve virtual machines now. So we regenerate the API, which queries this Solr index of our classes, and what we get is an Open API spec that has stuff about our virtual machine APIs. So it's got all of these APIs, and we have a db-create.sql script, which has virtual machine. This was generated with all of our columns based on their types and our foreign key relationships with hub and with cluster, for example. Got to add one for the project as well. Haven't got around to that. So we have that. And now we just have to restart our application. Let's check if everything compiles. So we go to, let me check which directory I'm in. I'm in AI Telemetry, so I do maybe clean install. And this is going to do some additional code generation with the Vertex API service libraries that build the rest of the code based on your open API spec. That's why we've, so you wonder, is this spec-driven development? Well, we have defined our open API spec through our code comments here and defined our API in this kind of definition. And then we've defined it through stacking these vertebraes with some disks here. And this is what creates our whole API, this kind of information. So our code compiles. Isn't that a miracle that AI can generate code that actually compiles? That's the best part of this. That's what 20 years of building the rules for this can do, is build a really stable framework for generating code. And then we can run this because it was completely broken before because we deleted all this code. But now we can run it again, and it's going to do the import process for virtual machines that we've defined in our hub ENUS API service import class, virtual machine data import. So I've already written this import process based on our generated code. So these vars, this is a generated public static final string that was auto-generated for us based on declaring this cluster name inside of virtual machine.java. So we declared this, but in the virtual machine gen.java, it created this helpful public static final string so that we don't have magic strings within our API. We can reference those, and we'll see, because this is a compiled language, if there's any mistakes that we've made. If we refactor things, we'll find things that break, because if you change the name of cluster name, it's going to change this variable, which will disappear, and then it'll cause errors in your import code for virtual machine resource. So this is kind of what the import process looks like. We reach out to ACM Observability to query virtual machines total. Actually, it goes to the Prometheus keycloak proxy, which is a secure proxy with fine-grained access control to OpenShift metrics. And we query virtual machines total for a hub. And we query virtual machines total for a cluster. And we import virtual machine data in this method. And we do access control and query the Prometheus keycloak proxy with our credentials, service account credentials, and then we import reactively through the Vertex event bus. Through event bus messaging, we can import each of these virtual machines that come from metrics reactively without blocking. It's all asynchronous and reactive. And we import all that data, and what we get is this page where we see all 15 virtual machines running. Oh, now there's 16 actually. There's 16 virtual machines in the Mass Open Cloud, and they're all available here in an access controlled user interface, as well as an API. And we can do all kinds of cool things with this API. We have some built-in tools to filter on things, and you can see what clusters these are in. So some of these 15 of these virtual machines are in the NERC test cluster. Whoops, I gotta be careful what I click on during this demo. Oop. There's 15 in NERC test and 1 in the local cluster. Oh, that's a good question. And then virtual machine names. So here's the names of them. They're all unique. So you see the number 1 means there's only one of these with this name, but here there's 15 that are in NERC test. So this is faceting. I mentioned that earlier. So we have all kinds of data about this that we can sort and graph and things, and create some other cool graphs like we do. So we'll create some cool metrics for this. You can see where our virtual machines are running because we've added some geolocation data to it from where the cluster is. Some other cool stuff about AI telemetry is that we have cluster data, so you can see the observability for our clusters. And this also has built-in access control. So if I go to Keycloak now and I log in as an administrator and I go to our realm called NERC and I go to users, Computate, and I go to groups and I leave this admin group, then what you're going to see here is fewer clusters. I have access to these 11 clusters, but now if I refresh, I only have access to NERC-OCP test. And if I view virtual machines, then I see the virtual machines in NERC-OCP test, but not the local cluster anymore. And if I go and leave the group for NERC-OCP test and then refresh, then I see no virtual machines and I see no clusters. But if I go to projects, I can see these two projects. So this is multi-tenancy, fine-grained access control that is very secure and very customizable within your OpenShift cloud environments. So hope you try it out. Check out AI Telemetry and start learning how to do some spine programming. So I've been talking for a long time. I'm going to wrap this up. Thanks for joining. Hope you enjoyed it. Happy Halloween.